So something kind of bad just happened. Um, it's made me want to put my mind off of it and do some admin of code. Um, the lighting is not going to work, and my phone is not set up as a camera, so I don't have my camera turned on, and I still need to put on some music. There we go. And I gotta sneeze. Okay, I sneezed. Woo! Um, so what just happened is that I've had a leaky steam pipe in my unit for a while, and my leasing office was informed about this a while ago, and they haven't fixed it yet. So today, after work, I sent an email. I was like, oh, this leaky steam pipe is still leaking. And I thought I wasn't going to hear anything about it until tomorrow. And then all of a sudden, my doorbell was ringing. Like, held ringing. Like they were holding it down for like a solid 15 seconds at 7:30 p.m. I was like, what the hell is this all about? And, oh, I guess I can put on my little image. There we go. And I'm gonna wiggle it as I'm talking. So I'm like, who the hell is ringing my doorbell at 7:30 p.m.? And I even checked Amazon to see if there was like a delivery coming in soon. And there wasn't. So I was like, oh my gosh. I live next to this bar, and I've had some issues with ding-dong ditching. So I'm like, these fucking kids again, ding-dong ditching me at 7:30 p.m. So I put on a jacket and I ran outside, and there's this man standing there leaning on my door, and I just opened the door with force. I'm like, what's your problem? And then he's like, whoa, this 2R? I was just ringing for 2R. And I'm like, yeah, I'm 2R. What's your problem? And then turns out he was a plumber trying to fix my pipe. And then he's like, okay, I'm gonna go. And I'm like, no, wait, I do want my pipe to be fixed. I'm so sorry for being so rude to you. Anyway, he couldn't fix it. He has to come back tomorrow. He was incredibly timid the entire visit. Understandably so. I mean, I would hate to be in somebody's apartment who just asked me what was my fucking problem. So yeah, that happened. You win some, you lose some. You win some, you lose some. Ay. It's one of those situations where I'm like, I mean, sure, I did something wrong. I was like way too aggressive to this guy. I think based on the circumstance, it is understandable because I have had people ding dong ditch in like very similar situations, and I've never caught them. So seeing somebody actually there after I thought somebody ding dong ditched me was like, you know, it was like, I finally got them. So I was like all riled up about it. Well, anyway, let's do some admin of code. I still haven't done day 17. I still haven't done day 17. So let's just read through this with like all the time in the world and be real careful about not missing anything. There's a 3-bit computer, which is a list of 3-bit numbers. So every single number, well, let's not make any assumptions. Okay, first of all, let's close everything that has to do with day 16. There we go. So let's split by comma, and then just print the first number to see if that works. Oh, okay. What? That doesn't seem right. Oh, I opened the wrong input. So that's going to be 2024 17, I think. Huh, that is super short. That's kind of insane. Okay, so again, we do split by new line, and then we take a look at S1 split lines, I think. So this should now be replace this with nothing. So now we should get the first number. Great. Oh, wait. Now we should get the first number. Okay. And then we get the 3 registers as a second value. So we take S0. And then we LMAP. Oops. We LMAP row 2 R split 1. And then I think we LMAP this one to int with a split of comma, maybe. Wait, no. There's only one number in there. What am I doing? That's gonna be int of this, right? Nope, list index out of range. That's strange. How's that possible? So we get s dot split new line, and then we take LMAP of every row. Oh, I see. Split lines. Yeah, that's more like it. Okay. So now we got T1, which is a list of 3 integers, and the first one is very big, the other one's a 0. Great. Okay, 8 instructions. 0 to 7. So how about we do A, B, C is T0, 1. And then for ints in T0. Let's just see, make sure this works. Great. I think I should do something like an instruction band, because we will consume a different amount of things. Number called the instruction pointer identifies the position in the program. It starts at 0. I think we call this the program. There we go. And I think I'm gonna copy it. All right. From which the next opcode will be read. It starts at 1. Except for jump instructions, the instruction pointer increases by 2 after each instruction. If the computer tries to read in an opcode past the end of the program, it halts. Def run program ABC program I. If I less than 0, if not 0, I return none. while true. If run is not break. Okay. And then I think we probably return 2. Because that's the default increment. There are 2 types of operands. Each instruction specifies the type of its operand. The value of a literal operand is the number itself. Combo operands represent literal values. What is a combo operand? For example, the value of the literal operand is the number 7. There are 2 types of operands. Each instruction specifies the type of its operand. The literal operand is the number itself. The combo operand. Okay, why is a combo operand still able to specify a literal operand? That doesn't make any sense. The number is the value in the A register. By 2 to the power of... Okay. Opcode is program of I if opcode equals 0. Then we do something with 2 to the power of combo of this shit. If I plus 1 greater equals... Well, it's never going to be greater, so we should just check for equals. We return none. There we go. Combo, ABC, and then we got program of I plus 1. There we go. Def combo, ABC with commas between. And then we got register, or I guess we can call it an opcode. If opcode smaller than 4, right? It was 0, 1, 2, 3? Yeah. Return opcode. And then next up, we have 4, 5, 6. ABC opcode -4 is reserved and will not appear. Great. Or opcode greater 6. Is that right? 6 minus 4 is 2, 0, 1, 2. Sounds good. Okay. All right. So that sounds about right. We do A divided by this one. It's probably a full number division. Truncated to an integer and then written to the A register. Great. A is equal to this shit. So we probably need to do jump ABC is equal to results. Okay, opcode 1, bitwise XOR of B and the literal operand. Man, this is really reading comprehension, isn't it? If opcode equals 1. Okay, what was a bitwise XOR? So instead of opcode, it's going to be just this, I guess. And then we do XOR with it. And stores it in B. BST calculates the value. I've had my screen shared the entire time, right? Yes, I have. All right. Wait, can you see my terminal? Probably not. I think I should turn this little guy over here. That's better. All right. Nice. Yeah, that's better. Okay. BST calculates the value of its combo operand modulo 8, then writes it to B. You got it, boss. 2 combo and writes it to B. Modulo 8, I think. Yeah, yes, probably. I kind of want to do get combo and define a lambda. Get combo equals lambda of this. There we go. Calculates the value of its combo operand. Writes it to B. Jump instruction 3 does nothing if A is 0. Jump if A 0, return to ABC. If it's not 0, it jumps by setting the instruction pointer to the value of its literal operand. Return something minus I, so that we have so that if we add it to I, it's going to magically become the right value. Turns the instruction pointer to its operand. Yeah, I think that's about right. Great. If this instruction jumps, the instruction pointer is not increased by 2. You got it. You know what? I think what's going to be better is to do this. And then to return I plus 2 and not 2. It's just a little cleaner. All right. Opcode 4, BXC. The bitwise XOR of B and C, then stores the result in B. BXC. For legacy reasons. That's insane. So we probably still need to return none because it's trying to read it. B equals to B XOR C, I think. Is that right? Calculates XOR of B and C and stores it in B. Yeah, that looks right to me. So what are we saying about reading a value and halting? Is it only... When do we halt? If the computer tries to read an opcode past the end of the program, it halts. So... man. I don't know, it's undefined behavior. It's not saying anything about... It's saying nothing about what happens if the operand is outside the program. But, you know, I think this is probably still right. All right, out. Calculates the value of its combo operand modulo 8. Combo modulo 8. 5. I think we should probably add a comment to all of these. 6, 7. There we go. Hey. Oh, there's no 7. I'm an idiot. There we go. All right. There is a 7. Jesus Christ. Better. Okay. Out. B equals get combo 8. Combo modulo 8, then outputs the value. If it separates multiple values, they're separated by commas. Ay. Well, how about output plus equals this? And then we return it. And then we do O plus equals O underscore print O dot, no, comma dot join O. Yeah. Huh? Maybe. I think we have a bit of a problem here because we can't join strings, integers, I don't think. We can only join strings. Okay. BDV. What is BDV all about? Exactly like ADV, except that the result is stored in the B register. You got it. So we take opcode 0 and we store it in the B register. Now, do we take the B register for the value or not? The numerator is still read from the A register. Okay, I guess not. So this is probably right. And then we got CDV. Works exactly like the ADV, except that the result is stored in the C. The numerator is still the A register. You got it. Okay. So I think we should be able to do this now. The first task is to determine what the program is trying to output. To do this, initialize the registers with the given values. Then run the given program. Always join the values produced by out with commas. After the above program halts, its final output will be this. Using the information provided by the debugger, initialize the registers, then run the program. What do you get if you use commas to join the values? It output into a single string. What? Once it halts, what do you get if you use commas to join the values it output into a single string? To use commas to join values. What the? Does it just mean we do this? Duplicate argument program and function definition? Program ABC program. Yeah, I think you're right about that. Okay. Cannot unpack non-iterable int object. IABCO. IABCO. All right. Are we ever returning anything that's not... what's happening here? That's probably better, huh? Not enough values to unpack. Got 4. Yes, that is true. I think what we can do is say return pointer equals I plus 2. And then we can just say, oh, in these cases, we just set the red pointer to this. And then here we return the red pointer. Makes it a little easier. So that's where I think you're wrong, because I think this number is in fact the right result. Okay, let's see. Yep. Non-surprisingly, 4, 6, 3, 5, 6, 3, 5, 2, 1, 0. Okay, once it halts, what do you get if you use commas to join the values it output into a single string? There's just this? But like, with commas? I've never, ever submitted a answer like this with like commas in it. Okay. So I guess we don't join it using a comma. We join it using a comma with the comma. Man, that was a bad instruction. What a bad puzzle, honestly. Digging deeper in the device's manual to discover the problem. This program is supposed to output another copy of the program. Unfortunately, the value in register A seems to have been corrupted. You'll need to find a value to which you can initialize register A so that the program's output instructions produce an exact copy of the program itself. For example, this are you talking about? Oh, it's supposed to output 035430. That makes sense. That makes sense. All right. All right. That's why today has such a low percentage of solutions, because this is a pretty tricky problem. Okay. The lowest positive initial value for A that causes the program to output a copy of itself. Well, I don't fucking know. How am I supposed to know? How am I supposed to know? So what are the instructions here? We got 0, 5, and 3. 0, 5, and jump. Jump jumps to 0. Unless A is 0. So we do the instructions 0, and 5 until A is 0. The instruction 0 does A divided by 2 the... Okay, that makes sense. So we take a look at the bits. We take a look at the third bit, except the third bit is not... The third bit is not actually 3, but it's... No, it is actually 3. Because the opcode is less than 4. Well, we could just run this until we get the value, but I'm 1,000,000% sure that that's going to result in an infinite loop. But, you know, just for the sake of it. Let's see. So we do this, but instead of this, we do test register A. And then, you know, we put A in here. And then we return this is equal to join string of I for I in program, right? I think that's right. So for, or rather, I is equal to minus, whatever. If test register I, print I break, I plus equals 1. So for this program, it's going to print 100,000, which is totally doable to like brute force. ASCR. Yeah, there we go. However, I'd bet $1 million that it's not going to be quite as easy for our real program here. Of course not. Of course not. So the right answer was, or rather, the right answer for part 1 was this, which has fewer parts than this value, which is amazing. Well, I'm sure there's like some bitwise shenanigans going on here. We could just try to like write out this number as a binary number and then see what we get out of it. So 6 is 4 and 2 and 0. 0, 0, that's 1, 1, 1, 0, 0. 1, 0, no, 1, 1, 0. 101, 101, 1, 1, 0. So let's see. I'm not sure. I think you can just do 0b and then this number. Yeah, there we go. All right, let's see what we get if we just run this. I mean, I'm sure it's not going to be right, but maybe it's going to give us some insights on if we're close. Let's see. So not test, but print. Print rich A and this long number. All right. So we have approximately the right amount of digits. We're 3 short. Let's just add 3 zeros to it and see what we get to. 3 more digits. 3 more digits. What if we divide this one by 2? Still about the same number. Divided by 2 again. Still the same number. Divide by 2 again. Still the same number. Divide by 10. Still the same number. Divide by 10. 1 digit too few. Makes you wonder. Okay, so that seems to affect that one. So now we got 2. What happens if we reduce this one by 1? 0. Okay. What happens if we reduce this one by 1? 6. That's interesting. That's very interesting. So the number goes up. That's quite bizarre. So there has to be some like modulo. Well, let's see. How about we start by taking the lowest number that gives us the right amount of digits. So, you know, we could just test this number and see what happens. I mean, we're not just gonna magically get to the right number, I don't think. But we might get some insights. Maybe we can do like a string similarity thing. Like the closer the string gets, like if we got any closer, we print the number. I'm gonna say, give me plus 1000. There's like a tiny chance we hit this. I'm gonna let it run for a couple of seconds. Well, why would this number go up if this one goes down? Because we're doing modulo. That's why. Modulo 8, to be precise. So we take a certain subset of 3 bits and we return it as an output. That's what this does. The entire time we always take a look at 3 bits at a time. And they have to be 3 consecutive bits. So how about we go back to working off of binary numbers. So what's the binary of this? That's the binary. Okay. So let's do not test reg, but print reg. And then this very long number. So now we're at 6. And if I, let's say, turn these into 1s, what happens then? Nothing. Let's turn these into 0s. Aha. So these 3 seem to affect, or rather these probably affected it. So if we set this 1 to 0, we might get a 2 at the start. There we go, great. So the first digit we got. Now we need to find out where the next 3 happen. Can I put an underscore in here without messing it up? I think I can, yeah. Let's see, I think it has to be powers. No, it's powers of 2, so I don't think this grouping makes any sense. All right, so we just locked in 3 values. Which one was it? I don't remember. I think it was these 3 right here. Let's see. I'm in the middle one, yes. So these 3 are now locked in. Great. Let's take a look at the 3 before. We got 101. What happens if we do 01? We lose 4. So this is the 5 in the second position. In the second position we need a 6. So this should probably be 001. 26. There we go. Oh, I don't know. Oh, I forgot to turn this back into a 2. 26. All right. Next one is a 3. Wait, we don't need a 6. We need a 4. What am I doing? We need a 2, 4. So it should be a 0 here. 2, 4. There we go. 2, 4, 3, but we need a 2, 4, 1. Let's see. This one is 3. Does this change it to a 1? Probably not. Nope. Does this change it to a 1? Didn't save it. Nope. All right, so then it has to be this one. Uh-huh. It's a 0 now. That's very interesting. Just because I said these. So what happens if I subtract 2 from it? It subtracts 1 from it. Oh, I'm an idiot. A 3 is only 2 ones and not 3. So it's these 3 right there that have to be a 1. It's currently a 2. So we're going to do this. And now we got 2 for 1. All right, we're making progress. 5. So 5 is a 4 and a 1. So that's this kind of pattern right here. Oh, wait. We need to lock these in. So I set a 1 right here. And we also set a different one to 4. So that these are here? Is it going to be 2, 0 now? Yes. Okay. So that's XXX right there. All right. Didn't save it again. 2 for 1. 2 for 1. 5 is the next one, which is a 4. So I assume it's probably going to be as easy as this. Yes, perfect. I think we figured it out. We just go backwards through the bit pattern. 7 is already a 7, which is these right here, I assume. So let's remove 2 from it, so it's going to be 5 now. Great. Now it's a 7 again. Next up, we got a 5, which is probably right now a 4. Yes, I don't even know which digit we're at right now. 5, 7, 5, 7, 4, yes. But instead it's 5, 7, 5. All right, so let's add 1 to it. XXX, 1. So now we got 2, 4, 1, 5, 7, 5. 2, 4, 1, 5, 7, 5. Next up is a 1, which is currently a 0. Now it should be a 1. Great. Next 3 locked in. Next up is a 6, which is currently a 4. That looks great. XXX, save it. We got a 6. Great. Now we got 3. 5, 1, 6. Oh. So we remove these 2. XXX. Great. CR. 60. 603. We got 602, so we add 1 here. Great. 603. Amazing. Well, I'm suddenly realizing that this string of numbers is way too short. That's a little concerning. Didn't we get the right amount of digits before? 603, 102, 603, 465, 530. That's not great. So what happens if I add a lot of ones before? Okay, now we're fine. We're adding digits as we go. So I'm gonna add 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's probably gonna add 2 more digits. It did not. Oh, it did. Yeah. I just had a different 1, 1, 1. Had a different reference point. Okay. Wait, how many digits do we actually need? So we got 603, and then after 603, it's 6 more. Great, so now we got the right amount of digits. Phew! That was a close call. Well, the last one is a 0, though, so that's not great. So let's probably add another 3? Interesting. Is the last one a 0? It is. Okay. So let's just leave this one in. And then we got 3, 0 at the end. Okay. All right. let's continue, shall we? So these three should be locked in. So we got another 1, 2, 3, 4, and then 1 bit. That's very interesting. Very, very interesting. Anyway, let's continue where we left off. 603, 603. Wait, do we have the right amount of digits? I feel like there's one too many there now. Ugh. Okay, now it's the right amount, but it's 30, and we got 70. So how about we remove another one? Okay, 30. Great, finally. Jeez. Let's double check and put this here and line them up. Yeah, great. All right. So we only have like 1, 2, 3 to fix. We can do that. No problemo. So 603, 1, whereas this is 603, 4. 603. I have a feeling it's going to be this one. 603, 3. Yes, sir. Wait, we don't need 3. We need 4. 603, 4. Six, 3, 4. Perfect. All right. 1, 6, 0, 3, 4, 6, 7 instead of 5. We've come to a bit of an impasse, I've realized. So this is the 6. Wait a second. That ain't right. Wait, what's going on? Okay. The last digit we fixed. 603, 4, 6. The last digit we fixed was a 6. Which is these 3, I think. And then we have a 7 where there should be a 5. So we just remove 2. Okay, we're back. We're so back, baby. 3, 4, 6, 5, 3, 4, 6, 5, and then we're gonna 7 where there should be a 5. We got a 7 where there should be a 5. Yes, all right. So now we got all the right things in here, but we probably don't yet have the right answer because it's supposed to be the smallest possible number. So let's experiment a little bit. So this one gives the right value. Let's just try setting some things to zeros. Doesn't give the right value. Does not give the right value. Does give the right value? Wait, now I'm second guessing myself. What even is the right ending? 530. 530. Okay, so this one did not work. This one did not work. This one did not work. Okay. And then obviously this one does not work. So we found all the starting digits. Wait, 530, but it's no longer a 5 before. It's 5530. 553. Okay. Yes, so these all have to be 1s to get 5530. However, these down at the bottom have not been set yet. 241. Yeah, as you can see, this is the exact same. So I'm going to say print this value. Too low. What the hell? I feel like we just established that it's not too low. Because this did in fact work. What? Oh my gosh. Wait. Wait. Oh, did I just do that for... Oh no. I did that whole thing. I just did that whole thing for the wrong input. Okay. I need a break. I'll be right back. God damn it! Okay, that was great practice for the real thing. Because we just did something incredibly pointless, which is to get the example input program to print the program for my actual input. How devastating. So let's just delete this thing here to make sure this doesn't happen again. Okay. All right, okay. All right, so let's check if we get the right amount of digits. This whole thing again. Wowee. Wowee. Okay, we do have the right amount of digits. And some of these even seem to be almost correct, maybe, perhaps. Okay. So let's start by finding A3. A3. Which is a 0, 1, 1. A 0, 1, 1. This one, perhaps? No. Maybe this one? 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 No. Maybe this one. No. That's all the threes. Ah, fun. This is so fun. All right, maybe this one. Nope. I am screwed. 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 Oh, man. I don't know how to fix this. Misalignment. Well, I guess it could potentially be bit inverted. I mean, these are 1, 2, 3, 4, 5, 6, 7 cases that we've tested. And neither of them fix the thing at the start. So yeah, let's take a look at bit inverted threes and see if these do something. Okay, that did do something. So it's one of these positions. So let's take a look at the first three. Not those. Let's take a look at the next three. Yep. So is it this one? Nope. So is it this one? Yeah. Okay, so by flipping this 0 into a 1, you turn this 3 into a 7. So this 1 adds 4 to that value. It doesn't really make much sense. Doesn't really make much sense. How would adding this one... What happens if we turn this into a 0? We get 3. So this one is the 4 digit. We're looking for 2. What happens if we turn this one into 0? Still 3. So what happens if we turn this one into 1? Now it's 7 again. Dude, I'm losing it. This is not gonna work. I need to actually understand the logic here. Oh, man. I don't really feel like doing that. I don't really feel like doing that. Let's just like flip random ones into zeros and see what happens. Well, it's a 3 now. Let's flip more into zeros. Still a 3, so that's not it. I feel like it has to be somewhere down there. Has to be somewhere down there. Still a 3. Well, we still got the right amount of digits, so that's nice. 3, 4, 1, 5, 7. Yeah, nah. That ain't quite right. That ain't quite right. So let's see. I mean, when does it flip from 2, 4, 1 to something else? We did get the bottom 2 digits right. And then, you know, a couple of random ones in the middle. It is definitely a little concerning that some of these bits now appear to be flipped. That is a little concerning. Ay, ay, ay. This might be one of those situations where if you just turn the code into Python, or like, you know, actual program code, instead of having it be stored as like a string in a register, you could probably speed it up to the point where you can just run it. Then again, how big is this number? 49 digits. What's 2 to the 47? Yeah, I think it's doable. I think it's definitely doable. To like run this number. I don't know, man. Maybe the best solution here is to program a machine learning algorithm that determines the combination between the input and the output bits. I should probably run like a pattern of ones and zeros and then like that same pattern's flipped and see what comes out of it. Because if it's just flipped, no, but there's XOR in here, right? There's lots of XOR operands. So that's not gonna cut it. So how about we take a look at all the operations, which means taking a look at every other number. We got 313, which is jump, BXL, J and Z, right? And 1 is this one, and then 5 is 0 is ADV. And then 5 and 6 are, I think, BDV and CDV. No, out and BDV. So what does this program do? Do we think it ever executes the values in the middle? Maybe, probably. Kind of scary. It's kind of scary. Man. I wonder how close we could get with like just random numbers. We got a whole lot of jumps. And then we got division and XOR. What does BXL do again? It XORs B with the next value. Well, it's a static value. So that's nice. And I think jump also jumps by a static value, no? No. All right. So we take a look at the, yeah, no, it is a static value, which is 5, 0, 1, 2, 3, 4, 5. Oh my gosh, it jumps. It actually jumps to the operand. Oh my gosh. Zero, 1, 2, 3, 4, 5. Yeah. That's great. That's amazing. We love that. We love it. And then it does a division. Then it does a jump to 6. 0, 1. I don't know why I took this thing down there. 0, 1, 2, 3, 4, 5, 6. Which again does a jump to 1. 5 is an output. You know what? That sucks. That really sucks. That makes this thing so complicated. I don't know if people are actually expected to like understand this whole thing. I tend to think no. But then again, how are you supposed to solve it if you don't? No idea. I'm just thinking. Man. It's tough. Like, well, the XOR only ever happens on B, right? And then C does get set. Okay, so there is definitely an XOR happening with like bits from the input. And how would we ever output? Because the output can be any of the 3 registers. So we could take something from A, put it into B, put it into C, XOR the 2 values, and then print it out. Oh, man. All the jumps are always if something is not 0. Yeah, if A not 0. The jumps are only if A is not 0. So I think we can assume that the jumps always happen, because otherwise the program is over. So that makes it a little bit easier. We do have 6 different jumps in the program. I think we probably have to write it out as a whole thing. Well, what we could do is just, you know, add a print whenever this stuff happens. And that way, you know, get the program into clear text. Just see the period of it, which, you know, there's only like 15 numbers here, so it's got to be a pretty short period. So 15 different instructions. Now that I'm thinking about it, it's definitely impossible to run this and brute force it, because the 15 instructions loop over the number, over every single bit. So if we have a 15-digit number, every digit is 3 bits. That's 15 times 3, 45. So that's 45 iterations for every single possible number. I guess it's not too bad. It could be worse. Could be worse. Yeah, I mean, we're only outputting 15 digits, and every output would be probably 1 loop. So it's not too bad. So we could definitely brute force it. Do we want to brute force it? I don't know. I mean, let's think about it pragmatically, because there's no way Topaz created all of these puzzle inputs by brute forcing. So there's definitely some logic to it. I wonder what the completion percentage is by now. Like if we take a look at the stats. All right, about 2/3 got it. 20 out of 25,000, 15,000 got it. It's not quite 2/3. It's more like 3/5. So it is doable. Of course it's doable. I mean, like, it's not impossibly difficult. It's a tough one. It definitely is a tough one. It's a tough one. I think what I'm gonna do, but not tonight, because my goal was to do this until 9 and it's 9 right now, is to print out, as the program is running, the instructions. So here it's going to print like a equals a divided by, and then have this one print the string. So we're going to have a new get string combo, which instead of this is going to literally return like either the number or the letter. I think that's going to help a lot, because it's very difficult to reason about numbers. It's a lot easier to reason about the program running. But yeah, I'm feeling a little tired today, so I'm definitely not gonna do this any longer today. I think there's a good chance I can get to it tomorrow, you know, plus the new puzzle for whatever tomorrow holds. And that's gonna be it for me today. I'll talk to you tomorrow, or potentially on Thursday. Have a good one. Bye-bye.